investigating simple harmonic motion over the next several days. Simple harmonic motion is a particular type of motion that is caused by, and it's going to be a lot of words, but I'll explain them, a restorative force that is proportional to displacement from equilibrium. Now, what does this mean? Well, you know what a force is. Restorative means that it points back toward the middle. So if your object is undergoing simple harmonic motion and it's horizontal, that means if you have some equilibrium position, if you move to the right, there's a force to the left. If you move to the left, there's a force to the right. And then proportional to displacement from equilibrium means that, well, it's proportional to displacement from equilibrium. As, if you go out, say you go 1 meter from equilibrium, you have some force. You then go 2 meters, the force is then twice as big. You go twice as far from equilibrium, the force is twice as big. That's what is necessary for simple harmonic motion. Simple harmonic motion is periodic. Periodic just means it repeats after a consistent amount of time. So there are lots of motions that are periodic that are not simple harmonic. For example, if I say I'm just tapping my pen, and if I do that at a consistent rate, say I'm tapping my pen once every 0.5 seconds or whatever, then that motion is periodic. The motion of the tip of my pen is periodic. It is not necessarily, it's probably not simple harmonic because there's no reason the force I'm exerting should be, one, always pointing back toward the middle. In fact, when I do this, I'm pretty sure I'm pushing the pen down up until it hits the notebook, and so the force is always downward, so it's not pointing back toward the middle of the motion. And there's no reason that it should be proportional to a displacement from equilibrium. Other periodic motions could be like you're dribbling a basketball. That you might be periodic if you're doing it at a consistent rate. But as soon as your hand loses contact with the ball, it's accelerating downward at 9.8 meters per second squared. And it keeps doing that until it hits the ground. And so that's a consistent downward force. It's not pointing back toward the middle. It's not simple harmonic motion, even though it is periodic. So you have to have a restorative force proportional to displacement from equilibrium. Now that is pretty much defined by the spring force. So a mass spring, if you got a mass on the end of a mass spring system will undergo simple harmonic motion. We know spring force is equal to minus kx. The minus tells us that it's restorative. It always points back. It always exerts a force back toward the equilibrium position. And then x is the displacement. So if displacement doubles, the force will double. So this fits the criteria of simple harmonic motion because the force is proportional to displacement from equilibrium. And that's true for a horizontal spring on a frictionless surface. That's also true if you have a vertical spring, if you have a mass hanging from a spring, then the net force is still proportional to displacement from equilibrium, where equilibrium is the point where the mass would hang at rest, which is where kx equals mg. If you pull it down farther, then the spring force is greater than gravitational force, so it would tend to spring back upward. If you push it up higher, then the gravitational force is greater than the spring force, and that would tend to cause a net. Then the mass would be pushed downward, and it would oscillate around equilibrium. So that's one example of of simple harmonic motion as an object sitting on a mass and oscillating up and down. Another example is a simple pendulum, which is we've got a string that's attached somewhere and then a mass at the end of the string. So for it to be a simple pendulum, there are a couple of idealized conditions. The string is light. An ideal simple pendulum has a massless string, as long as the string is light compared to the mass. Then we can say it's a simple pendulum. And we also need to say that the size of the mass is small compared to the length of the string. So in an ideal simple pendulum, this is a point mass. All the mass is concentrated at one spot. In reality, if you've got a string and the mass is much bigger, then the distribution of mass will affect things, and it will no longer be considered a simple pendulum. So this is less obvious that this would be simple harmonic, because the spring force is pretty straightforward, force proportional to displacement. So for a simple pendulum, think about this: what forces are acting on this pendulum? This is a vertical. I'm just drawing a dashed line here for the vertical. I'll say this angle is theta. What forces are acting on this guy? Well, we've got gravitational force, and we also have tension in the string. Okay, tension. And this will travel along an arc. That is part of a circle. It'll swing back and forth. The tension is directed inward. Tension is what would contribute to the centripetal acceleration of the ball. But let us consider the tangential direction. So I want to know, what is the force in the tangential direction? So tension is perpendicular to that, so there is no tangential component of the tension, but gravitational force, I can split it up. So this component would be the radial component, or the component that would contribute to the centripetal acceleration. This would be the tangential component, the one that would speed it up or slow it down as it goes along the circular path. This angle is theta, this angle is also theta, which means that the tangential component of the gravitational force is mg sine theta, and it's also negative because if our angle theta is in this direction, then that force is putting back in the opposite direction. Now again, this doesn't look directly proportional to displacement. However, we can say there's something called the small angle approximation. For small angles, sine theta is approximately equal to theta in radian, not in degree. And we can check this. Let's say, I don't know, what's a good angle that's small? 10 degrees. What's 10 degrees in radian? 10 degrees would be that many radians. And so there's that number, and then there's sine of that number. And look, 0.174, 0.173, they're pretty darn close. That's a very small percent difference. You can see that's a 0.5% difference between those two numbers. So for small angles, sine theta is about equal to theta. And we generally say this approximation is applicable up to around 15 degrees. Once you get above 15 degrees, it stops being a good approximation. But up to that point, it is reasonable. And then, as long as that holds, now our tangential component of force is mg theta. Now, technically, this has to do with rotational stuff that we haven't really talked about, but the angular displacement is directly proportional to the force, and more importantly, it's directly proportional to something called torque, that is the rotational equivalent of force. And because that relationship exists, we can say that the simple pendulum is simple harmonic for small, where the angular displacement is less than 15 degrees. So simple pendulum is simple harmonic for small oscillations. You don't need to know, don't worry about the math for this. I just wanted to show you where it came from. But remember that this is, the simple pendulum being simple harmonic is dependent upon this small angle approximation, and is therefore only viable for angles up to about 15 degrees. Okay.